Hello, my name is Philip, and in today's video we will show how magnetic fields work in currents, and we will show it on an example of two currents and how the magnetic fields of one current attract or repel the other current, and we'll show it on an example with actual numbers. So let's have an electron that's traveling like this. And the basic notation in electromagnetism in general is that the moving charge creates a new magnetic field around itself, but it has to be moving, right? So we have the moving electron, and it creates a new magnetic field around itself like this, and it gets weaker and weaker the further away you get from the electron. So let's show this on an actual current. So we have these electrons that are traveling to the left, and the direction of the current will be actually the opposite to the direction of the electrons, right? Because I don't know, so somebody just I don't know, it's just a notation. So the current is going to the left, but the charges are moving to the right. And now we will use what's called again we will use we used it in the previous video, but this is the different kind, I would say, of the right hand rule, and it looks like this. So we take our thumb, or we point our thumb in the direction of the current, and we wrap around the what's called like the we imaginary wrap around the current, right, the arrow, and we get the magnetic field that spins, not spins, but goes around the current. So it will look like this. And now the magnetic field will go to the infinity, right? The further away you get from the current, the weaker will be the magnetic field. And we can calculate the magnitude of the magnetic field only with the radius and the current that we have. And there is also this weird sign you can see there, and that's the permeability of the free space, right? It depends if the current is in the water or in the air or in vacuum. But for the examples that we'll show in a few seconds, we will use the constant of permeability of a vacuum. Okay, so we have two currents going in opposite directions to each other, and we also will need the radius, or how far apart they are from each other. And so let's say they are 2 millimeters apart, and we will also need a length, or let's say how much of the wire will generate the force, or will create the force. So let's say we have a length and the length is 3 meters. Now we will want to get the magnetic field of both wires, right? Or both currents. So the current one. So we take our right hand, thumb points down because the current goes down, and it wraps around. And the same for second current. So thumb up and it wraps around. So it will look something like this. Okay, but I don't really like this signs, or this arrows, this circular arrows. So we will use the signs, the X and the dot sign, as we discussed in the previous video. And so for example, in the second wire, in the I2, well, on the right side of the wire, the magnetic field goes inside the screen, right? So there will be the little X's there in the circle, and on the other side it goes out of the screen. So there will be the dots. So it will look something like this. And what we now want to get is the force that the second wire makes on the first wire, or the second current makes on the first current. And for that we will use this equation, right? The force, the force 1 to 1, the force that the second wire makes on the first wire. And if you watched the first video or the previous video, you saw this equation, right? Well, these two equations, the first one and the second one, are the same, because the velocity is actually equal to length, or the distance per time, right? And this is the basic multiplication, so we can also write it like this. And what is charge per time? Well, that's the current, right? The current is equal to how much charge will go through the wire in some time, and that's the current. So we can write it like this, and that's the equation that we got in the first line. Okay, so now that we've got this clear, we can calculate the force. So first we need to get the magnitude of the magnetic field that the second wire makes, well, in the radius of the radius that we got there. Yeah. So we just put the numbers in, and we get the 2 times 10 to the negative teslas. And now we can just plug it to the or put it into the equations that we get, and we get the 6 times 10 to the negative 4 newtons, and that's our magnitude. Now we need to get the direction of the force, right? And if the wires attract each other or repel each other, that's the main point basically of this example. So we have our right hand, right? And the first wire, sorry, the first wire is in the magnetic field to the left of the second wire. So the magnetic field points out of the screen, right? There is a tip, so it points out of the screen. So we take our right hand, the electrons or the charges move upwards, so index finger upwards, middle finger with our magnetic field, and now our thumb points to the right. So, and that's our force. So the wires will, if the currents are in the opposite directions to each other, the wires will attract each other. But now, what if we flip the current in the second wire? Well, the magnetic field will change, right? It will swap. And now, will the second wire, or sorry, will the first wire again repel or attract? Well, we can again use our right hand, so index finger upwards, and now the magnetic field goes into the screen, so middle finger into, and we have the force to the left. So now if the currents of both wires are in the same direction, the currents will repel. And while they won't be repelling, or the force, as you can see, is something to the negative 10 to times 10 to the negative 4 newtons, and it's pretty small, really. So that's why the cables behind your TV don't fly around and don't jump around, because the force is like it's nothing. But it's important to know that the force is there. And in the next video, or in the next episode, we'll use this, or not exactly this, but this concept to show how the electricity is made from the movement. And that's actually pretty interesting, and hopefully you'll be looking forward to it, and I will see you there.